Today we're going to talk about forces and free body diagrams. Now back in maybe grade 5, you learned what a force was and you were told that it was a push or a pull. And that definition that was good enough in grade 5, it's still good enough for IB physics. What we're going to take a little farther though is the idea that a force is the cause of changes in motion. And when we're talking about motion here, we're really talking about velocity. So if there's any change to the velocity at all, there must be a force involved. Forces are more fundamental than motion because the forces cause the changes in the motion. So if we want to understand motion, we got to study forces first. And there's three basic ways that a force can change the motion. In the first case, we've got the force parallel to the velocity. And if that's true, if they're both in the same direction, then the object is of course going to speed up. However, if the force is pushing back against the object's motion, if the force and the velocity are opposite in direction, then of course we're going to slow down. And then the third possibility is when the force is perpendicular to the velocity. And in that case, let's suppose we have an object moving up to the top of the page, we push on it to the right, then the object's going to change its motion like so. In other words, it's going to turn. So forces can change the motion in three fundamentally different ways. They can cause speeding up, slowing down, or turning. So we can classify forces according to the types of change in motion that they produce. But we also need to classify force in terms of what's physically producing it, its physical characteristics. And a key distinction here is between contact forces, where contact's involved, and non-contact forces. Another name for a non-contact force would be a field force. So for instance, there's a force of attraction between the moon and the earth, and that keeps the moon orbiting around the earth. But there's no contact between the earth and the moon. So this is a non-contact force, and the force is being exerted by a field, in this case a gravitational field. And the gravitational field is one of three main force fields that we'll study in this course. We'll study the gravitational force field, which is what gives everything its weight. We'll also later on in the course study the electric field force. And then after that we'll study the magnetic field force. Now for the contact forces, we have four main divisions. We talk about tension forces, and we want to think of tension forces as being forces caused by ropes. We talk about normal forces as being forces due to surfaces. We'll talk about frictional forces, forces that oppose motion. And we also talk about applied forces, which are just active pushes. Now, of course, physicists are lazy. They don't like going around and writing words like tension, normal, and frictional all the time, so they use symbols. And they'll typically use a capital T for tension or an F with a subscript T for tension. For normal forces, you'll usually see an N, a C, or a F with a subscript N. Frictional forces, a lot of variation here. Typically you'll see small f's, capital S with a subscript small f, or often an R for a case of a fluid friction or air friction. Typically for applied forces, a lot of variation here as well, but typically you'd see a P or a F with a small p or an F with a large A for applied forces. So let's look at each one of those four divisions in a little more detail. Tension forces are caused by ropes. So if you've got a rope in contact with an object, you're going to get one of these tension forces. That's the first thing. Second thing, fairly obvious as well, if you've got a rope attached to an object, then that force of tension has to be away from the object. You can't push an object with a rope. You can only pull. So tension can only pull away from the object. And the third thing is, let's say we've got a rope between two objects. Then the rope can only pull away from each object, so there's going to be a tension force this way on this object and a tension force to the left on this object. And those two tensions are going to be the same size because the tension in a rope has to be the same throughout the rope. And when we look at Newton's third law, we'll understand that a little bit better. So here we say that the tension throughout a rope is the same. When we talk about a normal force, the normal really means perpendicular to a surface. So a normal force is a force perpendicular to a surface. Usually it's kind of a support force. So for instance, if I have a bookshelf here and I place a book on top of that shelf, then the shelf has to support the book. And that force, which is perpendicular here to the surface, is what we'd call the normal force. If we had a wall and we placed a book against a wall this way and then put our hand against the book, then of course the wall here would have to exert a normal force to prevent the book from being pushed into the wall. So as soon as we start seeing surfaces, we should be thinking normal force. The key thing about all frictional forces is that they oppose motion. So for instance, in the case of air friction, which is an example of fluid friction, we could have a ball that's heading upwards, and of course the air friction, I'll use an R for air friction, would act in the opposite direction. It would oppose the upward motion. But then if the ball were on the way down, the air friction would act upwards once again to oppose the motion. So this is one of our key types of frictional forces called fluid friction. Another key type of friction is sliding friction, but it works in a similar way in that it opposes motion. And if we say have a block here and let's say it's moving to the right, then we would get a force backwards. I'll use a small f for that sliding friction, and it would oppose that motion once again. Be a little bit careful here though, because we could also talk about static friction. So this time we can have our block, but we're going to put it at rest. Then if we say put a rope on here and we pull with some tension force, there'll be a backwards frictional force that opposes that tension force that would have put it in motion. And until it starts moving, those two forces are going to have to be the same size. They'll have to cancel out, and that's why it remains at rest. Another type of frictional force is rolling friction, and we'll talk more about that later in the course. An applied force is pretty much exactly what you think of when you hear the word push. So if I were to push you, that would be an applied force. So an applied force is kind of an active push by someone or something. It's not passive the way the tension force and the normal force and the frictional forces are. It involves some sort of intention. And there's not much that we need to discuss with applied force because they're pretty much exactly what you think they're going to be. Now I want to introduce something called a free body diagram. And I'd say that the skill of being able to draw a free body diagram is one of the most important in this course. In fact, I'd go so far as to say if you're confident with free body diagrams, you're going to do well in this course. And if you're not confident with them, you're not going to do well in this course. Fortunately, free body diagrams are really easy, as I'll show you in a minute. So take note, free body diagrams are a critical skill. And the reason that they're so critical is really because a force causes motion. Well, really it's changes in motion. But we need to get at the force to understand motion. And typically in physics, we're really after the motion. So this skill of free body diagrams is going to be really fundamental, because what it's going to do for us, it's going to allow us to evaluate the overall force on an object. And once we've got that, then we can do some analysis and work out the motion. But this is our starting step. And that overall force, it goes by some other names. It's called the unbalanced force, the net force, the resultant force. Okay, let's try to do our first free body diagram. And we're going to do a free body diagram for this yellow block that's being pulled up a ramp by a rope. And I'm going to emphasize a very simple procedure, and I hope you'll see that free body diagrams are very easy. And that means you all should be able to do really well in this course. First step, draw a dot in the center of the body. Excellent, you're a star. Next, every one of our free body diagrams, at least right now in the course, is going to be a body on Earth, and that means it's going to have a weight. So let's draw that weight. The weight always acts straight down towards the center of the Earth. I'll make it, say, this long. And for a symbol, I'd either use a capital F with a subscript G for the gravitational force. I might just use a W for weight, or sometimes you'll see M times G, because the weight is equal to the mass times the acceleration of gravity. Next step, identify what is in contact with the body and draw the appropriate forces. So we have contact right here with the rope. And that means we have a tension force, and a tension force is always away from the body along the rope. So let's draw that in. There's my tension force. Where else do I have contact with that body? Well, there's contact right here with this surface. Contact with the surface means there's going to be a normal force. And that normal force is always perpendicular to the surface. So here's my normal force. Next step. Ask yourself, is there friction acting? And typically in the problem, they would tell you whether or not it's a frictionless environment or friction should be included. So let's suppose there is some friction. We know that our object's moving upwards, so friction must act to oppose that upwards motion, and it would go down the ramp. And I'll use a small f there, which would be a sliding friction. There might be a little bit of air friction as well, which would go in the same direction, and I use an R for air friction. Notice that if I have two forces in the same direction, of course I can't draw them both attached to the central dot, so I draw them in parallel. And the last step, which should be the easiest step, but is actually the step where most mistakes are made, and that is simply don't do anything else. Don't start drawing in velocities or inertia or anything else. The only way that forces can be exerted is by field forces or contact forces. We've done both of them. We've done our job. Now I have cheated a little bit here because I have lots of experience. These force vectors are supposed to be drawn to a length that's proportional to the size of the force itself. And I've got lots of experience with that. When we learn more about translational equilibrium and Newton's laws, you're going to get good at this as well. In the meantime, just make a guess, and if you think a force is bigger, then draw the vector as being longer. With practice and a little more instruction, eventually you'll get really good at this. Okay, let's get a little more practice drawing these free body diagrams and using our procedure. So we've got a bowling ball coming in, making contact with a bowling pin and knocking it into the air. I want you to do 6 free body diagrams. One for the bowling ball before, one for it during, one for it after, one for the pin before, during, and another for after. So a total of 6 free body diagrams. So pause the video, draw your free body diagrams, and come back for the answer. So let's start with step 1. Draw the central dot on each object. Done. Step 2, draw the weight vector straight down. So here's my weight vector for the bowling ball. I'll make the one for the pin shorter because, of course, a pin is less massive than a bowling ball. Same bowling ball, so I should have the same length vector here for the weight. Same pin, so it has the same weight straight down in all cases. That's step 2 done. Step 3, identify all points of contact for each object. One point of contact with the floor, one point of contact with the floor, 2 points of contact, one with the floor, one with the pin, one with the floor, one with the pin. 1 point of contact here with the floor, no points of contact at all for the pin while it's in the air. Now for each of those points of contact, let's draw in a normal force which should be perpendicular to that surface. So we've got a normal force perpendicular to the surface. So it's going to be straight up. Turns out that normal force will exactly cancel out the weight here. So you'll have no net vertical force, and that keeps the ball from popping into the air or digging down into the floor. And it works the same way on the pin. Normal force would balance out the weight. Even when it's colliding, that normal force still balances off the weight. And even after collision, it still balances out the weight. Here's the only place where the vertical forces aren't balanced, and that's when there's no contact. Now we're not quite done because we didn't involve that force between the pin and the ball when they're temporarily in contact. When they're temporarily in contact, the pin pushes back on the ball. I'll label that C as a contact force, but it's still kind of a normal force. It'll be normal to the surface of the pin. And likewise here, there would be a contact force with the ball. So the ball gets pushed backwards, causing it to slow down. The pin gets pushed forwards, causing it to speed up. And it turns out by something called Newton's third law that these two forces would be equal and opposite. So we've dealt with all the points of contact on all the objects. Our next step is to go to frictional forces, but we're told to ignore the frictional forces, and that means we can go on to step 5, and that means don't do anything else. You're done. These are the 6 free body diagrams that we've been asked for. Key points: the bowling ball moves forward the whole time, but there's no forward force on the bowling ball. And that'll make more sense when we study Newton's first law. And here we've got the pin in motion in the air. So the motion can be quite complicated, but the force is very simple. It's just the weight straight down. This time we have part of an IB question. I'd like you to follow the procedure and draw the free body diagram of the ball at the bottom here when it's in contact with the foot, and up here at the top of its path. So pause the video, try the question, come back for the answer. So let's start by drawing our central dots. Easy. Second, add the weight, straight down, easy. Third part, look for contact. Well, down at the bottom we have contact with the foot. We've also got contact with the rope. Up at the top, the only contact is with the rope. So let's start with our bottom diagram. We're going to have a force coming across this way. It's an active push, so we'll call that an applied force, FA. And then we've got the rope pushing straight up. So that's going to be a tension force away from the object directed along the rope. Now up at the top of the path, the only other force is that tension force, which is going to be along the rope. Now there's no other places of contact. We're neglecting air friction once again, and that means we've got to apply step number 5 and stop. We're done. Don't add anything else. That's all the forces involved. Okay, another question. This one involves an Atwood's machine. We've got two masses, M1 here, a little less than M2, so M2 is going to accelerate downwards, M1 is going to accelerate upwards. I want you to draw free body diagrams for each of the masses. So pause the video, try the question, come back for the answer. So let's start step 1, draw our central dots. Step 2, draw the weight downwards towards the center of the Earth for each of the objects. I'm going to make the weight of the big block bigger than the weight of the small block by drawing this arrow a little bit longer. Then we look for places of contact, and the only place of contact with each block is with the rope. So the only other force is going to be this tension force that's going to be away from the block and along the rope. So whatever the tension is here, it's got to be the same here. These two have to be the same length. The tension is the same everywhere throughout the rope. Here we can see that the tension is bigger than the weight, so this mass goes upwards. Over on this side, the weight's bigger than the tension, so this side it's going to accelerate downwards. Step 5, don't do anything else. And that's all for today, folks. Thank you very much.